Hi, my name is W. Kent Tabiska, and I'm going to provide an overall presentation on a program that we're doing called ARMAS. In particular, this system is a capability that we're building for doing radiation measurements from the surface of the ground up to low Earth orbit. Now, as you know, the background for space weather is that there's a dynamic radiation environment, including at aviation altitudes. And in particular, above 8 kilometers, the known radiation environment at this point is from galactic cosmic rays predominantly, as well as from solar energetic particle events that are often rare. We've also identified minor events at the secondary level from gamma rays that are due to precipitating particles from the radiation belts. Where are we at today in this overall development as a community? This slide shows us that, in fact, we're really at the end of this step 3 and going into a step 4. Step 3 is just monitoring, and step 4 is where we're getting into nowcast and forecast. And what step 4 really requires is an ability to have 24/7 continuous monitoring, as well as all the infrastructure to support collecting those measurements, assimilating them into assimilative models, and then providing that data out to end users. So in particular, there are several radiation-related program areas that we're participating in. As far as science goes, the team is supported by NASA LWS funding for the Radium project. That's just closing out at this point. And that's done the data assimilation of ARMAS into the NIRAS system. That has been implemented. In addition to that, from SET's internal research and development, we've implemented the Carry 7 FAA model for validation purposes. In addition, on the science side, from the NASA LWS funding source, we have partnered with UCLA to develop a machine learned version of the ARMAS database, and that work will begin here in the next couple months. For data collection, we've worked under a number of NASA SBIR as well as Air Force SBIR projects. In particular, the ARMAS FM5 instrument was developed under a lot of SBIR funding. And currently on our dual monitor SBIR, we're flying an ensemble of several instruments in order to measure the radiation environment, including gamma rays and thermal neutrons above the air traffic routes in northern continental US for a 30-day Worldview Enterprises Stratus-Light balloon mission in July of 2022. I'll talk more about this later here in the talk. Under the Air Force SBIR, we're now developing a high altitude drone. This UAV will fly at 20 kilometers and collect data for a year. We've been partnering with Near Space Launch and their SWAP-E program to put ARMAS Flight Module 8 dosimeters on their CubeSats. We're flying one already, starting in June of 2021, and starting in 2022, we'll fly 2 more CubeSats with our instruments there. And finally, I'll just mention that the SBIR Phase 2E activity with NASA has enabled us to partner with SkyCorp and their ISSI project to fly an ARMAS Flight Module 9 along with the Lunan SET instrument on the space station. That those instruments are delivered on December 10th of 2021 for launch. And I'll finally mention that we're building a new instrument entirely called the OPSRAD, and that's an LET detector that's under a NASA SBIR program. So I think I can report confidently that at this point, we've achieved a global baseline for radiation measurements. We've made 801 flights from 0 to 107 kilometers in the last 8 years. These are a number of the vehicles that we've been on that you can see on this particular slide. Now, one of the big science questions that's come up during the whole ARMAS program is why do dose rates at L shells between 2 and 7 and greater than 11 kilometers, why are their dose rates higher than the galactic cosmic ray background, even during geomagnetically quiet conditions? You see on the upper left panel, there's a yellow band in the northern and southern auroral zones. And these kind of designate the L2 to L7 regions where we see some excess radiation. Our measurements on the right panel show that, in fact, we get statistically a significant amount of dose above the climatological background. Climatological background is the blue line that you see fit through the data. The red line is the median value of all of our measurements for NOAA G0 conditions at 11 kilometers altitude. On the lower left panel, you see the NASA NIRAS model, and our climatological background fits nicely in the envelope of all the longitudes measured or modeled by the NIRAS system. And that really should represent the GCR background. So what is this source of excess radiation? Well, we're hypothesizing that we in fact have Compton scattering effects and also bremsstrahlung from the precipitation of energetic electrons coming in from the outer radiation belts, for example. That might be one process, and that process creates gamma ray photons as well as X-ray photons, starting at about 60 kilometers altitude. As those electrons are stopped, the atmosphere is transparent to those gamma rays all the way down to about 9 or 10 kilometers where they're absorbed. And the right-hand panel shows the GANT4 measurements or modeling versus the blue measurements of an ARMAS flight in October 2015 above the Ross Ice Shelf in Antarctica. This is a work that Guillaume Gronoff and Bruce Cherishani and his colleagues have done over the last few years, also showing that electrons precipitating into the mesosphere create resultant bremsstrahlung gamma rays. And these are different energies, of course, going from 0.6 MeV up to 20 MeV electrons. And you can also see that down at the 10 to 12 kilometer altitude, you do get some residual dose, and we believe that's that in fact is the dose that we're seeing. We've been participating with Bob Marshall and Wei Zhewu to do modeling of the X-rays, the gamma rays based on this bremsstrahlung ionization process. And here's a credit, I'm sorry, that's a typo, should say Zhu, XU. There's a recent paper in Space Weather Journal that has these results in it here. The dashed line down at the bottom shows for an 11 kilometer or 10 kilometer altitude flight that you need up to 10 MeV electrons to get that bremsstrahlung effect. So what are we going to do to kind of put this science question to bed? We're doing, first of all, a Worldview Enterprise balloon flight in July 2022. We're flying a number of instruments, and we're going to fly basically between Ls 2 and 4 in Idaho, northern Utah, northern Nevada, in order to be able to measure 30 days straight the environment. However, I'll also mention that there's a number of things that are going to happen in this program. We will also fly, underfly to that balloon during that period of time, at least one of our ARMAS FM7 devices on a commercial flight or business jet or ER2 during the July period to get the dose below the flight. Of course, the Worldview flight will be up at about 20 kilometers. And then in addition to that, in 2022, we have a drone system that we're building that will also be able to fly along a single longitude, but measuring at different magnetic latitudes, the radiation environment simultaneous with the balloon flight. On top of the atmosphere, we'll also have measurements from the TAGSAT satellite that we started flying in June. We're delivering to the space station. That will be launched in February, and that instrument will have both total ionizing dose and LET measurements on it. And it will be measuring during our Worldview Enterprises balloon flight. And finally, we'll also be later in 2022 starting the launch of 2 other CubeSats. So for the very first time, we will be able to measure the primary particles and energy coming in at the top, above the top of the atmosphere, and then down below the Pfotzer maximum, around 20 kilometers. We'll have continuous measurements 24/7, and then down at aircraft altitudes as well, we'll have measurements. So this will be the very first full-up column measured continuously for a period of time to be able to capture some of this energy coming in. I'll finish up by pointing out that we have a number of systems that we've built. This is the ARMAS Flight Module 7. It comes in its carrying case. We have an Apple iOS app that we've built to run the instrument and also display the radiation environment that comes out of the instrument. That app also has an ability for the general public to go out and get their current radiation environments based on whatever commercial flight or tail number or customizable pilot entered flight path that they put in. And this goes instantaneously out to our, from the app anywhere in the world out to our Radian database that uses both NIRAS and the assimilated ARMAS data, validated by the Carry 7 data. And then within a couple seconds, the data is returned back to the app as a flight path, as a radiation curtain, and then on a satellite view. I'll conclude by pointing out 2 major projects that we're right in the middle of finishing up. The deliveries for, so this is the ARMAS FM9 and the Lulin SET shown for the space station. And that instrument is delivered here in December 10th of 2021. It will fly to the station in February and be deployed in March for at least 6 months. In addition to that, I'll finally point out that our team at SET, one of our divisions, has been building a lightweight UAV. It will fly autonomously for up to a year at 20 kilometers. And its primary mission will be to do aviation radiation monitoring at about the 20-kilometer level above northern CONUS, continental US, as well as above the North Atlantic and the North Pacific air traffic routes. This particular CAD design does not have the solar array panels yet installed on it. That will be done during this next spring, but this will be powered by the sun, and we have a vertical takeoff and landing. It can take off at any location at any time, and then flip over from a vertical takeoff quadcopter mode into a fixed wing flying aircraft as it goes up in altitude. So with that, I'd like to recommend that if you have any questions, please contact me. I'm at ktabiska@spacewx.com. And thank you for your time.